सुअपराहन, सादा नमस्कार। मैं अनिल भारद्वाज आप सभी का पीआरएल के अमृत व्याख्यान के 98वें एपिसोड में स्वागत करता हूं, अभिनंदन करता हूं। I, Anil Bharadwaj, very warmly welcome you all to the 98th episode of PRL का अमृत व्याख्यान. This is also the 23rd episode of PRL का अमृत व्याख्यान 2.0, which we started on 30th of January 2023 after we complete 75 episodes of PRL का अमृत व्याख्यान, which started on 4th of August 2021 with the sankalp that we will have the Amrit Vyakhyaan every Wednesday at 4 p.m. every week. And that 75 episodes, uninterrupted episodes, got completed on 4th of January 2023. We are celebrating the PRL Amrit Vyakhyaan as a part of the celebration of Platinum Jubilee of PRL. And that is meant to showcase the history and legacy of work being carried out in PRL in the area of space sciences and physics. We called eminent personalities to deliver these talks, which vary from science and technology to education, to law, to management, to business, to sports, culture, music, arts, literature, and whatnot. Today, we have yet another very distinguished Vyakhyaan with us, Professor Hisayoshi YuriMoto, who is from Hokkaido University of Faculty of Science and Department of Natural History, Science, Earth and Planetary Science Systems. And he is going to talk to us on asteroid sample returns. And this is suiting the METMES conference also, which is going on from today morning. And we wanted to have the Vyakhyaan as a part of this conference, essentially because the topic suits very well to this METMES conference, which is focused also on looking at the sample return missions and what we got from previous sample return missions. We thank Professor YuriMoto to accept our invitation to be with us today and to deliver this talk in person. And I would now request my colleague, Professor D. Pallamraju, to formally introduce Professor YuriMoto to all the audience present over here, as well as those who have joined us live on the PRL's YouTube channel. So over to Professor Pallamraju.
Thank you, Professor Bharadwaj. It is indeed my pleasant duty to introduce today's Vyakhyaan Karta, Professor Hisayoshi YuriMoto. Professor YuriMoto is a highly distinguished and accomplished as a cosmochemist, planetary scientist with a wide range of research extending from the lightest elements, which from starting from hydrogen to core of the Earth in terms of oxygen and carbon that he has analyzed, looked to understand what's happening in the stellar formation, and he's a co-investigator and co-PI of several planetary missions, including the OSIRIS-REx, Hayabusa, and the latest asteroidal mission Hayabusa 2 to Rego. He's an accomplished and eminent mass spectrometrist who has investigated and pioneered several novel areas in cosmochemistry, meteoritics, geology and material sciences, environmental science, using secondary and mass spectrometer while holding several academic and research positions at Tokyo University of Technology and now at Hokkaido University in Japan. Is where he's serving as a distinguished professor. His innovative and novel ideas have led to more than 290 research publications that include more than 15 in science and more than 13 in nature. For his trailblazing research work, he has received numerous awards, medals, and honors that include a Sakaki Award, Geochemical Journal Award, Mineralogical Society of Japan Award, Geochemical Society of Japan Award, Leonard Medal of the Meteorological Society, Purple Ribbon, Hokkaido University President Award for Excellence in Research and Education, among many others. It's very apt that he has, is going to speak to us today on asteroid sample return, wherein several of the missions he was directly involved with. So we'll get a chance to listen to his experience and give us a first-hand impression of the experiment that are being conducted. So with this brief introduction, I'll request Professor YuriMoto to please come onto the desk. Thank you.
So thank you very much, Professor Dean, for your kind introduction. And yeah, before my talk, I have really high hopes for your Chandrayaan project and for the sample return by Chandrayaan-4 planned in 2028. I'm really interested in that project. So I will talk about today, I will talk about some asteroid sample return. So first I show no, next. Okay, thank you very much. So what is the asteroid? This figure is the planet orbit. The center is the sun, and Mercury, Venus, and this is Earth orbit. Then this is Mars orbit, and then this is Jupiter orbit. The orbit between Mars and Jupiter, there are many small objects. These are asteroids. So we call this one is asteroid belt. And you see there are spots scattered inside of the asteroid belt. We call this is near-Earth asteroid because these asteroids become to the Earth very closely. So this is the enlargement is here. And so I show two orbits of the asteroid. This one, red one, is orbit of Ryugu. And this white one is orbit of asteroid Itokawa. Hayabusa 1 went to Itokawa, and Hayabusa 2 went to Ryugu. this orbit is close to the Martian orbit, and then also close to sorry, okay, so I'm sorry, close to the Earth orbit. Therefore, it is easy to come to the asteroid. And this near asteroid is originally settled in the asteroid belt. And due to the high gravity of the Jupiter, gravity resonance produce these orbits change to this kind of near-Earth asteroid. So if we go to near-Earth asteroid, we can understand what is the asteroid. Okay, we show you the size of the asteroid. You know this map. This is satellite map. This is the Taj Mahal in India, and the garden of the Taj Mahal. So this is Itokawa. The side of Itokawa is the longest axis is 500 kilometers. So it is comparable to this length of the Taj Mahal garden. And this is the asteroid Ryugu. The Ryugu is top spin shape, and the diameter is about 900 meters. So it is larger, but still not so large. And this one is asteroid Bennu. Bennu is NASA asteroid sample return project OSIRIS-REx went to Bennu. The shape of Bennu is similar to Ryugu, but the size is half. This size is 500 meters. So asteroid size is very, very small. Okay, that's why it's small. This is a present asteroid. But asteroids, they formed. The asteroid is much more large. 4.6 billion years ago, asteroid was formed. And the size is about 100 kilometers. Therefore, size is smaller, about more than 2 orders of magnitude, because asteroid is some asteroids collide each other, and the impact is scatter the fragment from the parent body, and the parent body is reaccumulated or sedimented to the one asteroid. Therefore, present asteroid is smaller than their parent body. And the fragment is, each fragment is so small, so the accumulation style is not compact. So we call this is a double piled body. So there is a lot of spaces. So density of the volume density of the asteroid is about half of the density composed of the rock. Okay, next we show how we sample the asteroid. This is the sample return movie by Hayabusa 2. The ground is Ryugu. This is Hayabusa spacecraft. The spacecraft is down to the surface, Ryugu surface, and then as soon touchdown. Now, Okay, now touchdown. And the fragment is flying. A lot of fragment is flying. This is because the surface of the Itokawa or surface of the Ryugu is very fragile. So very, very fragile rocks composed of Itokawa surface, Ryugu surfaces. And next slide is how to sample it. The touchdown timing is about 1 second. At 1 second, the bullet is impact bullet to impact the surface, and the fragment is come to the sample capsule, and then the sample capsule is stored to the return capsule. So this process is occurred automatically. Then we find 3 grams of the sample. When we open the capsule in the laboratory, we found 3 grams of the Ryugu sample found in the sampling capsule. And another room, we found 2 grams. So total, we 5 grams samples recovered from Ryugu, asteroid Ryugu. So this is Hayabusa 2 case. But Hayabusa 1 case, the Hayabusa 1 failed the shooting of bullet. So the mechanism, so impact, we cannot make an impact. Impact the impact factor. Therefore, this is the Hayabusa 1 case. The capsule is the same. The diameter is about 10 centimeter. Oh, no, 5 centimeter. So you see, no samples. So there are no samples. Of the size, we can see by own view. So we try to find samples in this room 2 months for Hayabusa 1. So, but nothing we found. Then we cover the glass, silica glass on the sample, and then like this, and then it's reversed and hit by hammer. So we find very, very small particles on the glass surfaces. The size is average is about 10 micrometer, very, very tiny. And but the number is more than 1,000 particles. So when we analyze the Hayabusa Itokawa samples, we must characterize what is this samples. So in the optical microscope, the one particle is around here. So you see, this is transparent. So this is transparent minerals. And you see some opaque minerals. Therefore, this is minerals makes one rock. And in order to characterize, identify these minerals, we take X-ray CT. So this is density map of one particle, Itokawa particle. Then, in order to analyze these particles, we consider how to cut these particles. Then this plane is most favorable. So we ground polish this surface. Then similar contrast we can obtain. This is obtained by electron microscope. So there are several minerals. This color is olivine. This color is plagioclase, feldspar. And this color is pyroxene. And this is toroidite. And this one is chloride. So the mineral assemblage is similar to volcanic rock of the Earth. So we can determine this is terrestrial rock or asteroid rock. So we analyze the composition by EPMA. There is state-of-art EPMA is also installed in this institute. And using the EPMA, we analyze the ion composition of olivine and pyroxene. The horizontal axis is the olivine composition of olivine, shown as a ferrite content. The vertical axis is the ion composition of pyroxene, shown as a ferrocyrite composition, ferrocyrite number. And the average of more than 1,000 particles is here. So this composition is similar to LL box. LL box is one of the ordinary chondrites, LL chondrite. So chemically, this is similar to meteorite. Then we analyze many particles to determine oxygen isotopes. The oxygen isotope of terrestrial rock is different from the oxygen isotope composition of space rock. So we measure this kind of instrument. This is a big SIMS. Okay. Okay, this big block is magnet. The sample is installed to the sample box here, sample chamber here. Then ion beam is irradiated on the Itokawa surface, Itokawa samples. So Itokawa atom is sputtered out to go to the mass spectrometer. And then each of the ion is counted here. So oxygen have 3 isotopes. Oxygen 16, oxygen 17, oxygen 18. Therefore, we can count 3 oxygen isotopes simultaneously. Then I make this diagram. Horizontal axis is oxygen 18, oxygen 16 isotope ratio. Vertical axis is the isotope ratio of oxygen 17 over oxygen 16. And this is the region of the terrestrial samples. And red region is oxygen isotope compositions of Itokawa samples. So Itokawa samples plot compared to the meteorite. So as you expected, oxygen isotope composition of Itokawa is very close to LL chondrite. Therefore, isotopically and compositionally, we collect Itokawa samples. And Itokawa sample is very similar to ordinary chondrite. Ordinary chondrite is the most common chondrite found on the Earth. 80% of the meteorite is ordinary chondrite. So we recognize there is a variation. The plagioclasis blue is plotted here, this region. Olivine is black, is plotted here. And pyroxene red is plotted here, this region. This variation corresponds to the formation temperature of these minerals. So from this variation, we can estimate the formation temperature. And the temperature is calculated to 700 degrees. So this sample is metamorphosed at 700 degrees in the parent body. And in order to increase to the 700 degree, the parent body size should be bigger than 100 kilometers. So we can infer the parent body size from this analysis. And we measure magnesium isotopic ratios. This magnesium isotopic ratio, we can estimate the formation age. So this 0 is terrestrial value, and the plot is from Itokawa samples. The average is a little bit have positive value. From this slope, the error is large, but from this slope, the metamorphism occurred at 7 million years later than the solar system formation. Therefore, Itokawa parent body is formed very, very early stage of the solar system formation. So what is that? So how about the Ryugu? Ryugu have a lot of samples. So this is a creation facility. Ryugu stored extra. Now, at this time, this is just assembly. And the Hayabusa 1 is also similar kind of assembly. The inside the facility, dry, pure nitrogen is burned all over the time. But this part is vacuum. So the sample capsule of Ryugu is open in the vacuum. And then moved to hydrogen state and stored all the time. Therefore, at the measurement time, we can analyze the Ryugu sample under that condition to the space. So no aspect condition to the Ryugu sample. Okay, this is the he prepared the Ryugu sample. Ryugu sample is here, and this is a optical microscope to observe the Ryugu sample. And the inside of this box is purged in the very, very clean nitrogen. Okay, this is an example of Ryugu samples. The grid on back is 5 millimeter. Therefore, this size is about 1 centimeter particles. And you see, the Ryugu is very, very dark and black. Okay, this is an example of the carbonaceous meteorite of my laboratory. The texture is very, very different each other. There is some small particles in the meteorite, but no such kind of particles in the Ryugu samples. This is another meteorite. The color is similar, but still there are some kind of small particles observed in the meteorite. But such kind of objects we cannot observe on the Ryugu meteorite. So when I looked at the Ryugu sample, it must be similar to CI chondrite. CI chondrite is a special chondrite among the carbonaceous chondrite. So I asked to my friend Sarah Russell of Natural History Museum of London, and they have the CI chondrite. And I asked her to send one sample, and she answered okay. Then she sent this particle. This is CI chondrite. The scale is this grid is, the length is 5 millimeters. Okay, this side is very, very close to this particle. And you see the enlargement image is here. So you see the color is very different. But after the analysis, we recognize, we can understand this is the real color of CI chondrite. And CI chondrite on the Earth, in the museum, is changed to the original color during the storage. Our colleagues was very, very surprised. So Sarah Russell consider how to store the meteorites more carefully. So I will show you for what difference later. And we collected a lot of samples. So we analyzed the samples. Many researchers from all over the world. Our team is from Japan, Europe, US, and Asia and Oceania. So about 50 laboratories, and they are postdoc and graduate students. So this is the original plan. But as you know, 1 year later, of the sample return from Ryugu, asteroid Ryugu, pandemic, COVID-19 occurred all over the world. Therefore, original plan is changed. How change? This is the first analysis of Ryugu-san. Only 3 persons in the laboratory. Because the COVID-19 is prohibited. Many people cannot together in the laboratory. But we now, at present, recently, we have internet. So we connected by internet. And my young scientists have shown by the camera, mobile camera, to show how to do it, and we discuss online. So this is an electron microscope to observe the Ryugu samples. And the Ryugu sample there is several contrasts. Each contrast corresponds to different minerals. So we measure chemical composition. In nature, there are 83 elements in total. We measure and this side is the refractory element, and this is the volatile element. Most volatile element is helium. And the vertical axis is the concentration, normalized to CI chondrite. Why? To normalize CI CI chondrite is because CI chondrite is the composition is similar to Earth's sand atmosphere. Therefore, Ci chondrite, we believe, Ci chondrite have the average concentration of the solar system. So we analyze 66 elements determined and 54 elements by ICP-MS. The ICP-MS, very good ICP-MS, is also installed in this instrument. And I use XRF, X-ray fluorescence analysis to determine 39 elements. X-ray fluorescence analysis is very, very traditional analysis, but the analysis determines carbon, oxygen, silicon, sulfur. These element concentration is difficult to determine by ICP-MS. And the XRF determined by the tin and tel. And these elements is a kind of volatile element. Zinc is here, telluride is here, tin is here, carbon is here, oxygen is here, and sulfur is here. Why the volatile element concentration is important? Because Ci chondrite should be plotted to this line, value is 1.0, because the concentration is normalized to Ci chondrite. But the volatile element of the meteorite is depleted relative to the Ci chondrite. So these determination of these elements is very important. And this is the result. You see the volatile element plotted here. So no depletion of volatile element. So this is the this is strongly support. Ryugu is similar to Ci meteorite, Ci meteorite. But the average is above the Ci meteorite value, 1.2. This is because hydrogen is depleted. Hydrogen of Ryugu is 7%, and Ci is 20%. Therefore, the concentration of Ryugu is uniformly upgraded to 1.2. So we conclude chemical composition of Ryugu are similar to those of Ci chondrite. How about the isotope? Isotope signature of titanium and chromium is Ryugu is here, plotted here, and Ci is here. So this isotope is similar to Ci chondrite. This is a calcium isotope. Ryugu is here, Ci is here. So this calcium isotope also, this signature is Ci chondrite. So iron isotope and the titanium isotope. Okay, Ryugu and Ci quite coincident. And zinc, how about zinc and copper? The isotope of the Ryugu is close to the Ci chondrite. Then, this is the hydrogen isotope ratios. The hydrogen isotope ratio of Ryugu is similar to Ci chondrite, and also oxygen isotope ratio of Ryugu is similar to Ci chondrite. So all of the isotopic character support Ryugu composed of Ci chondrite. So when the CI chondrite is formed, Ryugu said the answer, provide the answer. This is a back electron image, scattered image of Ryugu. The scale is, this is 0.1 millimeter. And all of the minerals is secondary minerals. This means these minerals is altered by the fluid metamorphism. So there were fluid, aqueous fluid. And then these minerals is precipitated from the aqueous fluid. The background is clay minerals. This color is pyrrhotite. This color is magnetite. And this is a dolomite carbonate. We measure the isotope ratio by using SIMS. The SIMS can analyze the isotope ratio from very, very small minerals. So this is about 4 micrometer areas we measure. So from the oxygen isotope, the dolomite here, dolomite here, and magnetite is here. And the distance indicate temperature. So these minerals precipitated formed at about 40 degrees centigrade. And when the minerals formed, the answer is from manganium isotopes. Manganese isotope, manganese 53, is short-lived isotope, and half-life is about 3.7 million years. Therefore, the daughter isotope is chromium 53. Therefore, if we measure the chromium isotope ratio, the point is indicated to the formation age. And this diagram shows these minerals formed 4.2 million years later the solar system formation. Therefore, this diagram, this measurement suggests that parent body of Ryugu and CI chondrite is formed very, very early stage in the solar system. So let's see the Ryugu's history. 4.6 billion years ago, Ryugu was formed by accretion of rocky and icy materials. The parent body size will be 100 kilometers. Then, about 5 million years later, the ice is melted because the parent body is warmed at 40 degrees centigrade. And the hot water altered rocks to produce clay minerals. The body was broken to produce the present asteroid size of Ryugu. The size is 1 kilometer. The broken age, fragmentation age, we cannot determine yet. But at that time, we believe the H2O content of the Ryugu should be 20%. But now is 7%. Half of the water is evaporated to space. This blue curve is the step heating curve of H2O released from the Ryugu sample. The Ryugu sample at 600 degrees, most of the H2O is released biggest from the Ryugu sample. Why? This is because H2O included in clay minerals. The clay minerals have two H2O sites. One is in the structure, and another is the intermediate between layer and layer. And this water is placed in here. And the water, interlayer water, is placed here, and the evaporation temperature is 100 degrees. So let's compare the CI chondrite. You see, this intensity is similar to Ryugu. But this intensity of 100 degrees is much larger in CI than Ryugu samples. This is because Ryugu have, CI have interlayer water, but Ryugu do not have interlayer water. Why? Because interlayer is easy to evaporate. So in the vacuum conditions such as space, all of the interlayer water should be evaporated. Therefore, the water content in Ryugu is become 7%. So this is a real shape, real color of CI chondrite. And then the Ibuna is formed at 60 years ago. And this meteorite is carefully stored in Natural Museum History of London. But the sample is contaminated exhaust gas in the London. So it is the atmosphere contamination. So atmosphere contamination change the materials severely. Water content increase and color change. The reason of change color is most of the sulfur is oxidized to sulfate. Therefore, sulfate is released here, but Ryugu have very, very small SO2. So this is an indication terrestrial contamination so severe for the carbonaceous chondrite. And this contamination is become very difficult to find space organics because there is a lot of organics in the atmosphere, and the terrestrial organics is absorbed into the samples, meteorite. Okay, so therefore half of H2O is evaporated and 7%. And now arrive at the Earth here. And if we put on this sample on this table, after 50 years later, the color changes to this image. So we compare the history between Ryugu and Itokawa. The birth time is the same, 4.6 billion years ago. But the material is different. Ice dust is nothing in Itokawa. So, and metamorphed age is 7 years later. The body is much more warmer to 800 degrees centigrade. And then the body is broken to produce present asteroid Itokawa. The age is 1.6 billion years ago. And now we can collect the Itokawa samples. So this is the so what is the primary material of Ryugu? Ryugu have very small abundance of remain the primary material, but the abundance is very small, about 1%. This is the example. The olivine here and Ryugu samples. And these minerals, the oxygen-isotope ratio of these minerals is here. 60 rich minerals and 60 poor minerals. And we show the abundance histogram between 60 rich minerals and 60 poor minerals on next diagram here. So 60 rich minerals here and 60 poor minerals. The abundance is equivalent. The Ci chondrite is similar, but normal carbonaceous chondrite is here. So 60 rich minerals abundance is very smaller than this 60 poor minerals. But we know this abundance ratio is similar to comet samples. So Ci chondrite may be formed at the place, comet formation place, very outer solar system. So the similarity of oxygen bimodal distribution suggests accretion place of Ryugu parent body was similar to those of comet. And this supported by isotope ratios because Ci chondrite is isotope ratios of Ci chondrite is different from other carbonaceous chondrite. We infer the place is close to the orbit of Neptune or Uranus. And normal carbonaceous chondrite would be the orbit of Jupiter and Saturn. Okay, so time comes over. So conclusion. Laboratory analysis of return sample by Hayabusa, Hayabusa 2, and OSIRIS-REx reveal Itokawa is composed of material similar to LL chondrite. Ryugu is composed of material similar to Ci chondrite. Venue, I could not say about venue because this is not a NASA project. So the analysis is ongoing. So it is prohibited. I'm sorry. But the conclusion is venue is also composed of material similar to Ci chondrite. Ryugu and venue is very similar. So from this analysis, we conclude LL chondrite are derived from S-type asteroids. Probably other ordinary chondrites are the same. Ci chondrite are derived from C-type asteroid. The origin of asteroids, other carbonaceous chondrites, has not yet been identified because this is the abundance of meteorite fall. The ordinary chondrite is 80% of meteorite fall. And these chondrites come from S-type asteroid. Another big asteroid, sorry. Yep. Thank you very much. most abundant one is C-type chondrite. Oh, C-type asteroid. But we know C-type asteroid is Ci chondrite. The abundance of other C chondrite is much abundant than Ci chondrite. So what is the parent body? What is the parent asteroid of carbonaceous chondrite? This is Ci. So no, this kind of population we do not found in the asteroid belt. Therefore, we know little about the inventory of meteorites in space. So we need much more sample return from the asteroid to know what is the original of our solar system. And I would like to say again, I am very interested in your Chandrayaan mission. I'm very interested in new lunar sample in 2028. Thank you for the attention.
Thank you, Professor YuriMoto, for such an interesting talk. And I'm sure that everyone is taking back some piece of Rigo in their minds. So if there are questions, please, yes, Sujoy.
Professor YuriMoto, it was wonderful talk.
Thank you.
And my question is, if I understand correctly, you are proposing that there is the evaporation of water from the Ryugu sample.
Yes.
So have you noticed any vesicles at the surface of the Ryugu sample if there is the loss of volatile?
Yes.
So is there any vesicle signature? Have you noticed in the sample surface?
Okay.
Or inside the sample?
Yeah, the interior water easily to evaporate. So Ryugu, the surface temperature of Ryugu is about 100 degree because during the during the daytime, because the orbit, the closest orbit is similar to the Earth. Therefore, as you know, the moon surface is 100 degree at the daytime. So that is the same for Ryugu. So the evaporation heat energy comes from the 100 degree. Therefore, the interior water is evaporated.
I had a question regarding your aluminum 26H, because you have told about 7 million years, but the error bars were significantly large.
Yes.
So how precise is that age of 7 million years?
Okay.
And an excellent set of data.
Okay.
Everything is there, oxygen isotopes, you have done so many analyses. I wish we could do the same on the lunar samples. And excellent presentation. But that's my question. Thank you.
Yeah. So yeah, yeah, you are right. So we cannot the age precisely, not precisely. So it is the counting number is very, very small. That's the reason.
Probably that's the upper limit, yeah?
Pardon? Upper limit. Yeah, that's right. So if we believe that the slope is correct. Okay.
Okay, Professor YuriMoto.
Yeah.
Yeah. So first of all, thank you so much for such a wonderful talk. I thoroughly enjoyed it. I'm not from this background. I have two simple questions. So most of your interpretations are based on the chemical composition of the sample you collected. I'm curious to know whether when you are collecting sample from one place, how do you know it is uniform for the whole asteroid? I know it is very challenging to collect multiple samples, but how do we know that sample which is collected from one place, it is uniform for the whole asteroid, 100-meter asteroid, you were saying that?
Okay, so we now at present we know two observations for C-type asteroid. You have the two androcyte legs, and these observations, spacecraft observation, with the sample collecting sample is representative samples of the body. So therefore, and the spectral type is a little bit different, but both is typical C-type asteroid. Therefore, in our knowledge, the C-type asteroid is 100% Ci chondrite. So it may be true if if we assume it is true. Our answer is Ci chondrite is very fragile. Therefore, the meteorites enter to the atmosphere. Most of the Ci chondrite is spread out, and we cannot collect the Ci chondrite as a meteorite. This is our present probable answer. And the other Ci chondrite is we don't know, but some kind of very small population of the asteroid. But before the Ryugu and Osiris-Rex sample return, we believe other type of the carbonaceous chondrite is dominant in the asteroid belt. So our idea should be changed and should be re-evaluated in the future.
That is another very simple question. You said that at 40 degrees centigrade, rocky material convert into clay. So one of your conclusions was...
Please speak slowly.
Okay. One of your conclusion was that rocky material changed to clay at 40 degrees centigrade for Ryukyu asteroid. And for other one, it was 700 degrees centigrade.
What?
We're talking about the temperature calculation.
Yeah.
So at 7, Itokawa was 700 degree.
Itokawa is 700 degree.
It's at lower temperature.
For 40 degree.
So he says that, why is that different? Or the
No, at such a low temperature, means rock can convert to clay.
Yeah, okay. It may be different of the parent asteroid side, and forming accretion time may be different because the heat source is aluminum 26. So aluminum 26 is half-life is 70 million years, 7 million years. No, about 0.7 million years. So if the Itokawa body is accreted earlier, the heat source energy is high, therefore become high temperature. So this is the answer. Okay.
Professor YuriMoto, for a good talk.
Yeah.
I have a totally different question. I mean, more on observational point of view. From your laboratory analysis in Japan, do you have any idea about the surface porosity of the material, the regolith? The porosity of the material.
Yeah, porosity.
How porous it is?
Okay, porosity of the materials is very simple. So yeah, we have a centimeter or millimeter size particles, and we measure the 3 X-ray CT to determine the volume, and then we use microbalance. So this is a method we determine the volume density. And volume density is about half of the rock density. So therefore, 50% is vacancy.
Okay, thank you.
Yeah. So can I ask a question? Yeah. So very nice talk, and it's good to see the amount of effort you put in estimating all this. So I have a maybe very naive question from astrophysical point of view. So you estimated the size of the SAM, like the parent body is around 100 kilometers, right? So how do you estimate this?
Okay, this is the temperature and metamorphic age. So we
No, the you get a sample very little size, and then you said this parent body size can be of like 100 of kilometers, right? So how do you estimate that the parent body size was 100 of kilometers?
yeah, because we know the metamorphic temperature and we know the age of the metamorphism. From this data, and we know we know the energy source. It is aluminum 26. Therefore, we can calculate the parent body size.
Yeah. So basically, are you assuming like that if the size is 100 kilometers, there should be some gravitational pull, it is collapsing, the temperature will be rising, that kind of thing? Okay. Okay, got it.
Yeah.
Okay. Thank you.
I have one question. Yeah.
Yes.
You said that at 40 degrees centigrade, the clay disintegrated and the water released. And also from isotopic composition, you said that the parent body was at the cometary region.
Yes.
Okay, so then when this got released, means water got released from the material. When it was in the cometary region, or when it came to and I mean in the orbit of this orbit, present orbit.
Okay, water ratio, we do not, it is very difficult to estimate. Therefore, we do not.
It is supposed to be
but the
present condition.
Water content should be affect to the heat capacity. Therefore, the calculation is make more difficult.
If that is the case, if it has happened during the present time, then it should be surficial.
Yeah, so this is rough estimate.
Yes.
So the order of estimate, we believe it is correct.
Yeah.
Samples from the surface, yeah?
Yeah, sample from the surface. Yeah.
Thank you very much for such a nice talk. Your study made me puzzle for one thing. So you said the Ryugu surface, it undergoes evaporation and therefore water content is 7%. And whatever therefore isotope concentration, element concentration that you use, which is normalized to CI chondrites, bit higher. But CI chondrites are also undergo contamination and it has a higher water content, 20%.
Yes.
So what is exact water content of the original water content in the solar system material or nebular material then?
Okay, so that is a very good question. So the diagram is we normalize the CI chondrite in the museum. Okay, so therefore all of the element is higher. But so how to analyze the real water content? So yes, so the question is, what is the real? Okay, so in the sun, hydrogen content is much higher than the maximum estimate of the CI chondrite. Therefore, CI chondrite is already depleted in hydrogen. Therefore, if you consider what is the bulk composition of the solar system, we cannot. It is not meaning how precise determine the CI hydrogen is. But if you consider to meteorites is we need some standard in the meteorite. The highest hydrogen content is recommended. So we need more samples.
Thank you so much, sir, for your informative talk. I have a very small question. It's regarding, you have compared the CIs with Ryugu. I was wondering if any study has occurred on comparison between CR chondrites, which are also heavily aquously altered, and similarities with Ryugu, if any.
Yes. So okay. Very precisely, CI have variations. Therefore, each CI is each different. But I believe some variation and Ryugu or Asteroid venue should be close to the average of among the CI variations.
So actually, I was wondering about the CR chondrites.
What is the CR? Okay. CR chondrite is very different from the CI chondrite. So the isotopic composition is different. So therefore, the accretion place should be different.
Thank you, sir.
YuriMoto-san.
Yes.
Wonderful talk. Look forward to discussing some of it over dinner. There's so many questions. Something that I'm just wondering, the Ivona meteorite that you got from museum in London.
Yes.
If it gained 13% of water by sitting in the museum, how is it reflected in the oxygen isotope composition?
Yes.
That should be very different.
Yes.
To the CI and the Ryugu,
yeah.
right?
That's a good point. And so oxygen isotopic composition is surely different between Ryugu and Ivuna. So the Edwin UCLA measured the oxygen isotopes of both samples, and he found there are differences. So, and the difference is the oxygen isotope chondrite of Ivuna is closer to the terrestrial oxygen isotope composition.
And if I can just ask one more, which might be of wider interest.
Yeah.
You said about, you mentioned about Grand TAC scenario.
Yeah.
I was thinking these two asteroids, Itokawa and Ryugu, they are near-Earth asteroids. Coincidentally, their parent bodies appear to be 100 kilometers in size. Coincidentally, or we know probably better now because of aluminum-26, heating period was also 5 million years. 5 million years is the heating period, because of the aluminum-26 when it was live. But one came from the outer solar system, Ryugu, and Itokawa probably was inner solar system material, right?
Yeah, Itokawa is a different one, so it is inner solar material.
But does it put any time constraint on the Grand TAC movement?
Okay, so yes, I know. Grand TAC model introduced new idea for our communities, but I think it is not necessary Grand TAC is correct. so it must more. We have a lot of data, so much more discussion should be necessary.
Okay, ma'am. Thank you very much, sir. I have two basic questions. regarding origin of the asteroid belt. There are two school of thoughts in order to origin of the asteroid. First thought is that there must be a planet which collapsed and makes the asteroid belt. Second is that within the planetary nebula, there must be fragments of rocks and ice dust that not going to do accretion and that remain the same as present. So which theory you favor?
Please, I cannot.
Talking about a very elementary question of formation of asteroids, basically. So we say that there is an asteroid belt between Jupiter and Mars. So it is from the planet collision of planet and breaking up and making asteroids, or just the planet being formed?
Okay. So traditionally, as you say, two models.
Yeah, they are.
It is material to form the one planet, or one planet to collide it to small pieces. But now we know S-type asteroid and C-type asteroid with different materials and different parent body. But the S-type asteroid and C-type asteroid exist in the meteorite belt. Therefore, it is impossible one planet to collide to form the small object in a meteorite. But so and so he said some grand tuck model. Grand tuck model is that is a trash of the small asteroid. So asteroids formed everywhere in the solar system, and then Jupiter and Saturn is picking up to move into such areas. That is a present style of our knowledge. But I don't know this is really correct or not.
So can we call the comets as an asteroid? Can we call the comet as an asteroid?
Can be called an asteroid?
Yeah, I think the comet forming, it is okay. The comet forming place is close to the Jupiter orbit. That is my answer. So comet is one of the asteroids.
Okay, sir. Thank you.
Thank you so much, Professor YuriMoto. I know there are a lot of questions that we really want to ask Professor YuriMoto, and we can take an opportunity of this during the dinner if you are around, because Professor YuriMoto is going to join us. So you still have time to ask him lots of questions. With this, we would like to again thank you, and I would request Professor Bharadwaj.
Thank you very much.
To offer him a small memento from PRL and METMES. Thank you. Yeah. So in 5 minutes, we are starting the next session, which means you are supposed to sit here. No break, that means. So yeah, I invite Bhala to give vote of thanks for the Amrut Vyakhyaan.
Thank you, Kuljit. Good evening, all. With this, we have come to the end of the 98th PRL का Amrut Vyakhyaan, and it is a pleasure to propose the vote of thanks in a special colloquium on the day one of MetMes, which also coincides with the birthday of Edwin Hubble, who said the universe is expanding. Similarly, so the colloquiums on special samples from asteroids in a conference also expand our knowledge. So thank you, Professor YuriMoto, for your special talk today. Equating million miles to milligrams is quite difficult, but thanks a lot that you showed us how to do it. And with the meteor and meteoroid, there's the conference that is going on in PRL. Yeah, so it's a meteoroid that you have taken and it is analyzed as a meteorite. Right. For the researchers from international researchers and people from within the country, you've come a long way. And you'll see that today is the 98th colloquium, which means there were 97 colloquiums before this. It's not that you have missed all the 97 colloquiums. If you go to PRL YouTube page, you can see that we have got all the colloquiums waiting for you, and you can go through whenever you find time. And there'll be more colloquiums coming up. So thanks to our director PRL, Dean PRL, and the organizers of MetMes, especially the people behind the scenes, the young colleagues of PRL. And from this colloquium, we know that even the samples from million miles can be returned. So we request that you all return for the next colloquium and also for the next MetMes that happen in PRL. Thank you. Yeah.